Okay. All right, everybody. We're very fortunate today to have Professor David Kipping visiting us from Columbia University. He does a lot of different research, mainly on observational signatures of exoplanetary systems and how you detect them. In addition to exoplanetary systems, he's worked very extensively on moons, which he's going to be talking today, but also exoplanetary rings, and even recently like mountains. Like he's also done some work characterizing stellar hosts, and he's done a lot of interesting work on statistics and even information theory on exoplanetary systems. He got his undergraduate degree at Cambridge University, his PhD at University College London, working with Giovanna Tinetti. And after he got his PhD, he was a postdoc first at the Harvard Smithsonian Institute, and then later became a Sagan and Menzel Prize Fellow at Harvard College Observatory, working with Dimitar Sazalov. And if you guys don't know him, he's a very big name in exoplanetary geophysics. So now he is, in addition to being a professor at Columbia University, he is also a research associate at the American Museum of Natural History. And today, we're going to be hearing about his detection of an exomoon. So, yeah, thank you.
Thank you. Yeah, thank you for that kind of introduction. Yeah, I was certainly going to cover this exomoon discovery or claim of evidence for a possible exomoon throughout this talk. But as you can see from my title, I don't want to exclusively focus on exomoons, even though it's probably what I'm most well known for. It's actually what I spend, I'd say, probably 10–20% of my time actually working on. So I want to try and advertise some of the things we've been working on, in particular, really the search for the weird. So I think in my original title I sent around, it was the strange. But essentially, I'm interested in the weird, and why I've changed the word from strange to weird is not just because of this comic which I found, which seems to really capture it, like the stars are wrong. I actually gave this comic to my student, Adam Wheeler, who did a project. And usually when a student finishes a project with me, I like to give them like a parting gift. And his project was all about looking for the weird, and I'll tell you about that today. So this was the comic that I gave him. So why is the weird worthwhile? Why is it interesting? Well, I think the weird is always kind of the most exciting stuff in a way. It's always the things which you haven't anticipated. And of course, in the history of astrophysics and astronomy, we've seen that happen time and time again, from the detection of the first pulsar to the recent evidence for these fast radio bursts, for which the origin is still unclear as to what these things are, and of course Tabby's star. Of course, the common thread of all of these is that when they were first announced, people thought maybe it was aliens. Like pretty much every time, like even back in the pulsars, it was called Little Green Man 1 for a while, as you probably know. So, and certainly like these two have had a lot of recent speculation about them being aliens. I'm not really focusing on that today. I'm just really interested in how do you detect these type of signatures in the first place. And in particular, this is a challenge because I think in most of these instances of these serendipitous discoveries, they're done by eye. They're done by a person who just happened to be looking at the right data set at the right time. But as we get into this era of ever larger data sets, we're going to need to do a bit better than that. We're going to need to automate our techniques for finding strange things. So that's kind of a running theme throughout my talk. Actually, you might not think exoplanets are weird, but they did used to be weird before I studied exoplanets even. So this is when I was at college. I remember hearing about exoplanets being discovered, and 51 Pegasi b was, of course, a very famous discovery in 1995 by Didier Queloz and Michel Mayor, pictured here. And hot Jupiters, especially, which this was the first hot Jupiter ever found, a 3-day orbit, Jupiter mass planet, very close to a normal star. That was, I don't think too many people had really anticipated such objects would exist. You have to be careful to say never anticipated, because someone will always email you and say there's this Russian paper from the 1920s or something. But it definitely wasn't a mainstream idea that there should be a population of these things. And indeed, actually, the origin of these things is still kind of a mystery, still up for debate. And in a way, exoplanets remain kind of weird, even with these hot Jupiters. But in 2 decades, a lot has changed. And there's this great, if you're on Twitter and you follow Eric Mamajak, he posted this about a year ago, I think now, where he showed a plot of planet discovery rates as a function of time. And what you can see is that this is on a log scaling. So this is like a Moore's law of exoplanet discovery. So you can actually have a doubling time of 27 months if you fit a straight line through this on a log plot. And that holds, in the Kepler era, the pre-Kepler era, and of course now we have TESS and Plato on the horizon. So it seems like there's good reasons to think this should last for a little bit longer at least. And what's scary about it is that if you extrapolate it, you end up with 1 million planets by 2034. And when I saw that, I kind of, even though I'm in the field, I had to pause and think, what's the point of that? Like, what is the value of finding 1 million exoplanets? What do we really learn from such a large sample? Are we just doing this for the sake of it, or actually are we trying to answer some question that we can only answer if we have that number of objects? And I think it's important that we don't just keep building more and more transit surveys without actually pausing to ask that question. What are we actually trying to do with these vast data sets? So one philosophy might be what I call the 1%ers philosophy. That, in fact, maybe it's even more extreme than the 1% of the 1%, but only the very closest and brightest stars. This is a depiction of the nearest stars to the sun. I think this is the nearest 10,000 stars, although because of the contrast, you can probably only see a couple of dozen here. But basically, the philosophy is that only the nearest stars, things like Alpha Centauri, Proxima Centauri, Barnard star, those are the objects which are worth spending our resources on. Everything else, it really doesn't matter too much. And in a way, that's kind of the philosophy of TESS a little bit. Their primary mission is to measure the mass and radii of 50 Earth-sized planets. So they're going to discover way more than 50 planets, but their primary mission is really just about the top 50. That's it. So you have to wonder, what about the rest? Is there no value in those, or do they have something to teach us? So that would give you the other philosophy, maybe, which would be the big data philosophy, that what you're doing here is you're collecting a census, you're doing demographics, and that those populations is ultimately what's going to teach you the most. It's not going to be the 1%ers, it's going to be these large populations. Those will give us the deepest insights, and we're hopefully one day going to know about, just as we know about many, many stars throughout the galaxy and the different distributions, we'll know about all the different planets scattered throughout as well. Well, finally, the third philosophy I'll throw out there is this kind of the theme of my talk, really, I guess, which is the weird things, the needles in the haystack. This is, of course, Oumuamua, or an artist's depiction of Oumuamua. This cigar-shaped interstellar asteroid, or potentially cigar-shaped, that's still under debate. But this is obviously kind of a one-off and an interesting exception to the rule of most asteroids that have been discovered. And amongst these very large number of data points, these millions of exoplanets we will find, perhaps there will be Oumuamua-esque objects, not in the sense they're interstellar, but in the sense that they grasp our interest because of their bizarre properties. They have something so exceptional about them, and we're only going to find those exceptional objects if we have a catalogue of 1 million planets to work with in the first place. But then that raises questions about how you even spot those weird things in the first place. Okay, so these are the 3 different approaches I might put down here. Maybe you can think of others. They're not mutually exclusive. It's not like one's best and the others don't really matter. They're all valuable and complementary. But I would say it's probably worthwhile pausing, especially if you're at the beginning of your career, as to which of these philosophies, especially if you're in observations, you're kind of pursuing, you're following. Because I think in any field, whether you're in exoplanets or whatever you're doing, you're probably thinking about one of these strategies at some level, whether you realize it or not. Okay, so I'm mostly going to talk about this, needles in the haystack. But before I do want to say something about this. So even as I said, like I'm mostly thinking about exomoons, which I would say fall into this category of kind of the weird. But I also do like big data a lot, and I just want to advertise something we've been doing thinking about that. So fortunately, it's already been introduced, informatics. I sort of mentioned that in my introduction there. It was mentioned by John. So when we think about big data and looking at the populations of exoplanets, this is pretty much what most people in the field are doing. They're taking populations and looking for correlations between, say, the size of the planet and the type of star it's going around, or looking for clustering analyses, for instance, mostly frequentist statistical tests. This is a plot from Lars Bacave doing something like that. He's using actually a sliding KS test here to try and see if the metallicity distribution changes for different types of planets. And he argues, in fact, here in this Nature paper, there was 3 types of planets, 3 categories of planets, if you like, doing this analysis. So that's a fairly common technique. Definitely the metallicity versus planet population thing, that's been hit over the head many, many times by many different authors. Another approach is to try and go Bayesian. It's kind of tricky to go Bayesian computationally because if you just look at a single object, say I'm looking at a single planet and I want to fit that with a Bayesian model, I have to fit for maybe half a dozen, maybe a dozen free parameters. If I want to fit a population and do it rigorously, then I have to do something called a hierarchical Bayesian model, where I have this set of, oops, I'm kind of tying myself down here. I have this set of population parameters at the top, and I have these individual parameters for all my objects. So this could be the masses of each object. So if I have 1,000 planets in my sample, there'd be 1,000 free parameters in here, 1,000 radii, and then some controlling distribution parameters which sit on the top. Almost pulled my laptop off there. This is actually an example from a paper we did a couple of years ago. I was actually advertising this paper earlier. But this is a mass-radius relationship where we just take all the masses and radii of planets where it's been measured to good precision, and we fit a probabilistic model for that distribution. And you can use that now to, if you want to predict radii or masses, you can use this relationship. So that's one approach, but it is very challenging, I have to say. Dealing with 1,000 free parameters is very non-trivial. It's very difficult, even with modern computers, to do that. And a third approach, which is slightly different and hasn't been touched on too much, is this is Claude Shannon pictured here, is to think about information theory. Is there ways that we can use information theory to have some insights? So I'm not the only person who's thinking about information theory, but I'm going to highlight a paper I wrote recently about this topic, where really I would say the goal of this project is just to try and start people thinking about using it more seriously, because these two techniques are pretty much the bread and butter of most people in the field right now, but I think there is some value in thinking about how we can use information theory as well. Okay, so the setup for this was pretty much these two systems. These are two Kepler systems that were discovered back like 2012, 2013. And this system doesn't really blow anyone's mind. It looks pretty boring. This is the inner planet. It's about the size of a super-Earth, and then we go out to sort of a large Neptune on the outside in the chain. Don't worry about the spacing is kind of arbitrary, but they're in rank order. But the Kepler 20 system kind of blew everyone's mind because it went big, small, big again. So it was kind of strange, especially from a solar system perspective. Didn't look intuitive as an architecture for a planetary system. So when I looked at that, I immediately thought, this seems to me like an ordered system. There's something about it, just intuition. It seems like an ordered system, and thus you might call it a low entropy system in the information theory jargon. And this seems like a disordered system, unless it should be high entropy. So I could give it those labels, but that's not really quantifying it in any way. That's just a hand-wavy statement. So I tried to find some way of actually quantifying this statement. Okay, so one approach, or maybe the simplest approach you might think of, in terms of just purely their size orderings, which is all I considered here. I wasn't really considering the spacing ratios or anything like that. Just the size ordering is that if the next planet along is bigger, I'll give it like a tally score of +1. If it's smaller, I'll give it a -1. And I just go along and count up and end up with a score of +4 here. And if I do it for this system, it ends up with 0. It evens out. And there's actually many, many ways of getting that. You could swap those two around. You could swap all these objects around. You can keep swapping them. There's many different permutations. And in fact, there's 66 ways in which you can rearrange these objects and still get a tally score of 0. There's only one way you could get a tally score of +4. That's exactly like this. So this is in our way, therefore, of measuring or defining an entropy, because the standard Boltzmann entropy is just the Boltzmann constant multiplied by the log of the number of ways. So I don't worry about this constant. I think that's an interesting thing to consider. Maybe you could use like the variance of the sizes or something as a scaling factor in front here. I don't use that. I just focused on the log W to characterize these entropies, which I'm writing down here. Okay, so we have a way of defining entropy. That was for a 5-planet system. There's 66 ways of getting a tally score of 0. There's only one way of getting a tally score of +4. And there's also one way of getting a tally score of -4. And there's these intermediate states here. And I can do this for all different multiplicities. I did it up to 10, and then I got fed up of keep going, because you start to get some very large numbers. But what's neat is that you don't really have to go beyond 10, because if you just copy and paste these numbers into Google and say number sequence, it will actually figure out what this is. Kind of amazing. This is called the Eulerian number series. I don't really understand why it happens to explain this pattern, but it does explain it very well. And I even tested it on I created like a 15-planet system just to make sure it worked, and it really does seem to work in a general sense. So you could generate the number of ways and thus the entropy for any state you want using this expression. However, the big thing that bothered me about this scoring system, of this tally scoring system, is that if I apply it to the solar system, which I've depicted here, this would make the solar system very high entropy. It has a tally score of -1, so almost right in the middle, close to 0, and thus there's a very large number of ways of getting that. And then I thought, well, maybe that's just because of Mars. Mars in the grand tack scenario was sort of truncated, and it really wanted to grow bigger, but Jupiter stopped it. So what if I let Mars go bigger, and it became a super-Earth, as it may have done, had it not been for the grand tack? Even in this idealized solar system case, I still get the same number of ways. And maybe you can see why it is. It's because I go all the way up a staircase and then all the way down a staircase in terms of the sizes, so it cancels out. So a better way, at least a modification I propose, is to have some kind of, you want to include the autocorrelation almost, like a memory of the previous scores along your ladder. And the one way I propose to do that is just to take the integral under this history of tally scores. So that's what I do. So I just calculate the area of how the tally has increased and decreased over time. And if I do that for the actual solar system, this dramatically reduces the number of ways. So we've gone from 15,000, i.e. a very high entropy, down to just a couple of hundred. If I do it for the idealized solar system, I get almost not quite down to 1, which would be your ultimate low entropy system, but certainly a very low entropy situation in this case. So in total, what I define each microstate by is by this subset, t comma I, or this vector t comma I, tally and integral.
How does this change when you add to planet 9?
Yeah, I'm not going to include planet 9 in this because that's too much of a controversial subject right now. I don't know. I guess it would probably be smaller than Neptune. So, but then it depends on whether you include the dwarf planets, etc., etc. So, this is somewhat of a cartoon picture of our solar system. But it was, I would say, it's certainly true that the inner 8 planets guided the way in which I devised these strategies. Yeah.
This might be, sorry, you're a little off, but is there a way to quantify with the sort of Italian integral possibility of unknown exterior planets?
I don't think, that's not something I've investigated using this system. I actually coincidentally have written a paper about that topic using deep neural networks as a way of predicting if there are exterior planets. So I'm happy to chat to you maybe afterwards about that. But I haven't really, actually it's an interesting idea. I haven't thought about using informatics for that purpose, but maybe there's something to be done there. The problem with doing this integral path approach is that it makes that Eulerian number sequence no longer work, and you get this very, very complicated number of microstates. So this row for this should be n equals 6, yeah, gets expanded out now into this sort of strange array of submicrostates. This is the number of ways again, and this is the tally and the integral score of each microstate. All the gray things I can't compute analytically. These curved lines are like equations I was able to figure out, basically reverse engineering and trying to see if I could get a general equation. But I couldn't find any general equation for these things in the middle. So I just make a pre-computed library and then use a lookup table when I want to compute entropies. But I would still love it if somebody could figure out what the equation was, because it still kind of nags me. This is like a 3D representation of all the microstates. That's a 1-planet system, and at the bottom you have a 10-planet system. I don't really know what the point of that is, except it looks cool. So what's kind of nice is that if you do some Monte Carlo simulations, you can actually prove that this entropy scoring, as indeed as expected, increases over time, or at least a proxy for time. So what I did here is I started with a low entropy system, a completely ordered system, and then at each iteration I give it a 10% chance to swap neighbors in this multi-planet system. I keep doing this for 10 to the 5 times, and then I take credible intervals over time. And what you can show is that, for instance, the low entropy state, 0, is never returned to. There's like a very, very low probability of getting things back to that lowest entropy ordered state if you just are doing random swaps in the system. And you also can see the general trend that entropy in both cases increases over time. It doesn't ever go down. Although, of course, you can have an individual object drop down, but it's very unlikely to go all the way down to 0. So I'm treating here the number of swaps as a proxy for time. It's definitely not like linearly proportional or even some simple function. It's just a cartoon way of characterizing how things might change over time. You could also consider ejections, for instance, on the system and things like this. OK. So we have this increase, and now we can actually apply this to real. This is just a histogram showing you that there's absolutely 0 instances in 10 to the 6. Expanding this to 10 to the 6, these are 10 to the 5 I showed you before. Even go to 10 to the 6, I couldn't get a single example of a low entropy system. And that's important because that Kepler 80 system I showed you earlier is exactly that. It's a 0 entropy system. And it's apparently no way you could make that via random swaps. That's not possible. So you could either have it born ordered and then just have no exchanges in position to get it to this state. Or I guess you could have it born somewhat disordered and have exchanges to make this happen. But what I'm claiming here is that this is very unlikely to happen by random chance. OK, so if we rule that out, I just want to add one caveat that I'm assuming there's no Maxwellian demons here. So I could always stop my Monte Carlo simulation. I'm doing 10 to the 5 steps. I could stop it at a particular low entropy state and put a hold in and just keep running the clock for, I don't know, 1 billion steps and say, if you hit low entropy state, stop the simulation. That would be a Maxwellian demon in this case. I'm assuming they do not exist. That there's no particular preference to stopping the simulation at a certain time. That's an assumption. OK, so my conclusions from this is that if you observe a system with low entropy, it's very unlikely to have emerged via random swappings, and thus it has some memory of its original architecture. OK, so it doesn't have to be perfectly ordered, but even a low entropy system has some memory, some connection to how it was originally formed. Now, that sounds like a very obvious statement, and I think when we look at Kepler exoplanets, we basically assume that. We basically assume that we can take these architectures and it's teaching us something about how they formed. But I'm basically doing all the hard work in a way of demonstrating that rigorously that this is true, that there are good reasons to think that this should be a valid assumption. And then I actually applied it to the Kepler data to see what it looks like. So what you're looking at here is a histogram of Monte Carlo simulations of random systems. So be careful not to pull this along with me this time. But these pink histograms are 0 entropy systems that I just scramble for a very, very, very long time and look at what the final entropy scores would look like. This is a 3-planet system. OK, so to break this down, there's a lot of information on here. So this is the fraction of random systems with this entropy score. This is the Kepler multis, these circles. That's the actual fraction of cases with those entropy scores. This is the subset of those Kepler multis which are also dynamically packed. So what I do there is I take the Hill criterion and I make sure there's no gaps for possible planets in between them. So in other words, they should be full. I shouldn't be missing any planets in between these, which is kind of important. But it turns out it gives almost exactly the same score in between. And this is the average entropy of my Kepler systems minus, plus or minus an uncertainty from bootstrapping. So in other words, you would guess from this that the average entropy is slightly lower than you would expect, like 2 sigma or something, 2.5 sigma. We can also do a p-value from Anderson-Darling test, which is a bit like a KS test, but a bit more robust. And you could also use a binomial likelihood function to define a likelihood of acquiring this, which is also kind of unlikely that this would happen by chance. And then I can do this for all the different multiplicities, and I can do it for the tally scoring, or I could do it for the integral scoring, tally integrals on these rows. And I can add this all up, go from 3 to 6 planet systems, and the conclusion is that Kepler systems indeed do seem to show lower entropy than that which you would expect from random swaps. Which again, I think is somewhat obvious, but it's nice to prove that is so. So I wrote this paper about this. Do Kepler planets remember how they formed? I guess the spoiler is yes, they do seem to. There's obviously a lot of things that I think that could be improved about this and could be built upon from this. I would really like to have some way of characterizing the spacings, whether the spacings are random or are locked into resonant integers, for instance, or commensurable periods. That would be an interesting test to do. And of course, I haven't really included that Boltzmann constant yet to account for variance and even the uncertainties in the measurements of the radii themselves. So there's certainly a lot that could be played around with this. This was really a paper introducing some ideas to hopefully get people's creative juices flowing about how we could use information theory.
So this is a bit counterintuitive because in stock also you have mass segregation. So the highest entropy state is where light masses are outside and the high mass objects are inside.
It's interesting you say that because I asked for some simulations from Elisa Quintana and Sean Raymond, who do planet formation simulation work. And in all of their simulations, they end up with very high entropy states. I actually didn't include it in the paper in the end. But I didn't understand what was happening. But whenever I used their simulations, all the systems had a much higher entropy than even random. It was higher than even random. They're in the very highest bracket of entropy. No, this is like take 10 million planetesimals and let them randomly dynamically evolve, and if they stick together, then you form a larger planetesimal, and you keep going until you end up with a solar system. So I was provided something like 10,000 mock solar systems from that process, and on average they had much higher entropy than the Kepler systems, and even slightly higher than random. So I didn't quite understand why that was so, and so I just focused on the Kepler data in this paper.
Yeah, but normally systems, when they start evolving, start collisionally or have ejections.
Yeah.
You have essentially a more sort of
Uniform
distribution of mass contrast. You get rid of the lighter ones easily. So the mass constants or the size contrast starts increasing.
Yeah, I changed size for mass because they don't record the size; they just record the mass. And it was just the objects which had survived after, I'm not sure, 50 million years of evolution or something. Yeah. So that would be another interesting experiment to revisit and understand what's really happening there. Okay, I want to come back to the weird if I can. And that's the needles in the haystack philosophy, because I think the exomoons is probably something you might think of as being weird. Actually, it's becoming more and more mainstream, but it's something which I've been looking for a long time and thinking about for a while. This is a simulation of six transits of it's not real data. If we had real data like this, it would be amazing. This is a very convincing exomoon detection if we had this. This is 6 transits of a Neptune with an Earth-like moon orbiting an M-dwarf. And it's a 12th magnitude M-dwarf as observed by Kepler. And they just basically don't exist. You have like a handful of M-dwarfs that bright observed by Kepler. But it gives you a very nice clear exaggeration of these features. You can see the companion moon very clearly transiting. Its duration changes quite significantly depending on its phase. You can see the transit timing variations of the planet. You'll also notice that whenever the moon's on one side, say it's on the right-hand side here, coming in after, the planet is transiting early. So you get like an anti-phase. And that's because the barycenter's right down the middle, of course, between these two objects. So we can look for these types of effects, and these are all basically anomalies of the transit, essentially. So that's why it connects, as you heard in my introduction, to rings. These effects aren't grossly indifferent to looking for rings, and even it connects, of course, to looking for perturbing planets in the system, which could equally cause these wobbles. Indeed, we found several new transiting planets, or several new planets that were responsible for transit timing variations during our hunt. Yeah.
How would rings cause wobbles?
Okay, rings don't cause wobbles, but they would cause shadows just to the outside, potentially. They can even cause a brightening if you have backscattering. No one's seen rings in Kepler data yet either. So we have this project that's been looking for these. When we simulate these, you have to be careful, not just to simulate TTVs using some analytic framework, because they are generally limited in accuracy. What you really want to do is photodynamically simulate the whole system. So that means that every time step, you really simulate a mini solar system, and you evolve it, and you compute the overlapping disks on the star, and you compute your fluxes, which is what this is doing. So that takes a bit more work, but it's worth it, because then you get a simulation which really encapsulates everything. Now, I am looking for the weird. I'm going through lots of Kepler planets trying to discover moons. But that sounds like a fishing expedition. And so if you're looking for Oumuamua, that is basically a fishing expedition. But is there a way you can design your experiment where even if you don't find anything, there's still something interesting to be said? And that was certainly something I thought about very hard when I was first designing this project. So we do this, of course, using Bayesian statistics, as you might have guessed, from this expression here. So this is our posterior distribution of the parameters we're interested in, theta. This could be things like the mass of the moon, mass of the planet, radius of the star, things like this. This is our photometric data we're conditioning on. And there's also an assumption of the model. That's kind of important. People normally omit that when they write down Bayes' theorem. But for us, it's very important because we are comparing different models to each other. Some with a planet, some with a planet and a moon, for instance. So this term at the bottom turns out to be one which is often ignored, especially in the planet community, but is very important when we're looking for exomoons. This is our Bayesian evidence. It's just the integral of the top. It's a normalization factor. It doesn't depend on theta, because it's marginalized over theta. And thus, if you're doing conventional inference and you only want theta, you could just ignore that, because it's a constant all the time. So if you're using MC, for instance, very popular MC package, it doesn't really compute this for you without tuning it quite a lot. Multinest, on the other hand, which is a package we use, I'm sure many of you have used it as well, will give you this for free. In fact, it's really the objective of the algorithm is to determine the evidence. In a nutshell, it does this by converting the integral into a trapezoidal sum. It basically casts a very large number of points in the parameter volume. It tries to draw a contour of constant likelihood, so it iterates for a while trying to find this contour. Once it's found it, it then shrinks that net down to a smaller volume and continues to do so. And at each step, it knows what the volume inside here is, and it also knows what the likelihood is, and thus it can compute, it can basically just do trapezoidal rule on this integral to compute the evidence. That's basically how it works. So we use this algorithm, so we're doing photodynamics and multinest, which, as you might guess, is very computationally expensive. It takes us about 50,000 CPU years per Kepler planet to fit them. A lot of time, but fortunately Pleiades has been very generous and gave us lots of time to look for these objects. These are the types of planets we typically pick on. This is the period, these are all Kepler planets. This is the period of the planet in days, the radius and Earth radii. We don't tend to look at hot worlds, things on 1 to 5 day orbits. And that's not because I put a hard cut here. It just kind of naturally comes out of imposing these two conditions, that the moon has to be tidally stable over 5 gig years. We have to assume some fiducial love number and Q number to do that. But assuming something reasonable, you can calculate the maximum allowed moon mass for 5 gig years. You take that moon mass, you convert it into a size, and then you say how detectable would that size be by Kepler. So if you're a hot Jupiter, the largest moon it can hold on to is typically like Ceres-sized or something, and there's just no way Kepler could see that.
Does the moon's orbital plane inclination with respect to the planet's orbital plane, does that factor into A at all with the oscillations?
I think the paper we use for these calculations is Barnes and O'Brien 2002, and I think they assume coplanarity in their tidal expressions. I think.
Also retrograde.
Yeah, that's right. It's a very fiducial calculation. It's by no means ruling out that there are exomoons here. It's just we don't think it's the most likely place to look. Okay, so we've generally looked at those types of planets, and we've been doing this for a while. Collecting 2 million CPU hours gives us about 60 Kepler objects of interest, Kepler planets. After looking at about 60 planets, we still hadn't found anything. But we were able to take our upper limits because it's not just a fishing expedition. We thought carefully about the Bayesian inference side. We can take our upper limits in each case and say something. It actually turns out that we do much better upper limits on the mass ratio than we do on the radius ratio. And that might surprise you because Kepler has detected very small planets by essentially the radii passing in front of the stars. And the reason is because when we do our fits, we allow for full 3D geometry in these orbits. And it's very easy to hide the radius of the moon. You could have the moon either inclined enough that it doesn't transit at certain epochs. It could be hiding either behind or in front of the shadow of the planet itself. And you have data gaps in the Kepler data which allow you to put the moon there when the rest of the time it's not. So it turns out that most of the time your radius posterior almost goes up to unity. It just says, well, any radius size is okay with me. I could always explain the data with a very large moon. The mass is much harder to hide because no matter where you put the mass in the system, it will always cause some kind of dynamical effect on the planet itself. And thus we generally end up with much tighter constraints on the mass ratio. Okay, so doing that, this is sort of the fraction of time we achieve the sensitivity in the y-axis. And so to give you an example, 40% of the time, 2 out of 5 cases, we're able to do Pluto-Charon, sort of 10% mass ratio. In 1 out of 8 cases, we're hitting Earth-Moon. As probably some of you know, this is way, way off the Galilean moon system. Galilean moon system is 10 to the minus 4. So this is encouraging that we're getting down to here, but a little bit disheartening that it seems like there's no hope, with Kepler at least, of finding Galilean moons this way. This sort of depressed me a little bit. The other hard thing about Galilean moons is now you have multiple moons and they wash out each other's TTVs unless you get lucky with the resonance trapping, I suppose. But generally, our model isn't even really fitting for that properly. It's essentially a uni-moon model that we regress to these systems. We can convert these into occurrence rates, but as you can see, they're not super impressive. But I guess these are the first occurrence rates that were ever derived for exomoons, so that's something. But we wanted to do a bit better, and so we started thinking about how we could capture these radii. There was kind of a neat idea put forward by a Hungarian group, Gyula Szabo and Attila Simon in 2011, and it was built upon a little bit later in 2014. And the idea was that if you stack many, many transits together, and you assume the moon is coplanar, that is a basic assumption here. Now, we are not allowing for full 3D geometry. Then the moon will just basically go from left to right, causing these little shadows. And thus, if I stack that signal, I would see some ensemble wing that I could potentially look for. This is a little bit difficult because you have to remove the TTVs first to do this, of course. You want to line things up really well. And you want to make sure you don't have any outliers. If you have one bad transit in here, it's going to really screw you up. You can't do medians for this type of signal because the moon spends less than 50% of its time here. If you take the median, it will be a flat line. You have to do mean binning. When you do mean binning, outliers are very important. So this makes it very, very challenging. The other problem you have is that these planets that we're interested in are generally long period. They're like 100 days. And Kepler only looked at most fields for 3 or 4 years. So that typically means I have like half a dozen transits. And this technique requires a very large number of transits for the stacking effect to really play out. So generally it doesn't work unless you stack different planets together, which kind of feels like you're cheating, but it's just asking a different question. We're now saying, rather than does that planet have a moon or a population of moons, we're asking, does this population of planets have a population of moons? So that's how we're kind of approaching this question. So together we looked at 284 different planets and we stacked all of their light curves together. There's 4,000 Kepler planets altogether. We started out with about 1,000 of these red dots. And we got down to about 300 that were like our pristine sample where we were confident the data quality was really good. But after like 2 years of working towards making that plot, this is basically the final result of all 284 stacked. This is the out-of-transit data, and I've sort of mirrored it on itself because the pre-transit and post-transit should be symmetric. So I've mirrored it over. And this is distance from I've rescaled time into distance from the planet in planetary radii. And you can see that there is pretty much a flat line here when you stack the data. The blue is sort of some draws from a Monte Carlo fit. The black is what you would expect if 100% of these systems had a Galilean clone moon system. So every single one of those 284 Kepler planets has the exact clone of the Jupiter moon system. That's what you would get, a 10 ppm effect. Very, very, very small signal to look for. And we can actually rule that out. That is actually excluded by our data. But it's not a particularly impressive constraint. It depends on your perspective. But our upper limit is that less than 40% of these systems have Galilean clones. But a Galilean clone is a very small moon system, so I guess we're doing pretty well in that sense. We have beautiful noise properties as well by stacking this way. We also tried slicing and dicing it, which is like, once you don't see a signal in the stack, the next obvious thing you do is you take subsets. We tried the smaller planets, the larger planets, the multi-planets, the single planets, the cold stars, whatever you want. We tried a whole bunch of slices. No matter how you slice and dice it, you can't get signal. You have to be careful that you don't slice and dice it infinitely, because then you will eventually get signal. So we tried to be a little bit conservative with the choices we made. What you can also do is just say, well, forget Galilean moon systems, just fit a single large moon around these planets and see how well you do, see what your best fit is. And you get these occurrence rate maps. So what we're essentially saying here is that a moon that's very widely separated from the planet, that's our easiest signal to detect. We can rule those out to like a 3% occurrence rate once you get up to like 2 Earth radii. So 2 Earth radii, 100 planetary radii separated moons do not exist. They're very, very rare. But once you start getting, these are actually the symbols for the moons in the solar system. Once you start getting down to, that's the moon over here. Once you start getting to the moons at 60 planetary radii, our occurrence rate is only about 1/3 at that rate, which is actually about the same that we got before using the mass technique, but using a completely orthogonal method now. The only thing that's interesting, if we take a map of the Bayesian evidences, red means it's disfavored, green means it's slightly favored. We do get this little island that's kind of interesting, and it would basically correspond to moons which are very, very closely separated to the planet, just a few planetary radii, and would be in between the size of, say, Ganymede and the Earth. So maybe super Ios, you might call them. I don't claim this is a real population, but it is interesting because they would be the last type of moons to survive during migration. It would be the moons which are really, really close to the planet, which would be the last ones to be stripped off in planet-planet scattering events. So it may be worth some further work to check out if this population is real or not. So that's kind of where we got to. What time do I have to finish? 3:10. Okay, thank you. So this is kind of our summary of where we're at with the exomoons. We haven't surveyed these objects. I've been chatting to people today about how it might be worth doing this, actually, looking for moons around hot Jupiters. We haven't looked. We've looked here. We don't think moons are common. And that basically tells me that either they rarely form. You have planets forming here, but they rarely have moons. Or more likely, I think, that these gas giants especially are forming further out, migrating in, and they're losing their moons in that process. So I guess the final thing to say about this is that it'd be really important to survey out here these very, very long period transiting planets. They're very, very precious because if you think about it, the probability of getting a planet that far out lining up is incredibly unlikely. We actually have about 6 Kepler planets out here, which are gas giant and around moderately bright stars and greater than an AU out. So there's literally like 6 to play with. So we would really like to hit these objects quite hard in the future where we're given the telescope time to do so. Yeah?
Would those exomoons also be easier to detect because the planets out there would have a really big hill radius?
Yeah. They can certainly support much more extended moon systems, and that makes it easier. It's a bigger lever handle to see those TTV effects. Okay, so you might have seen this and be wondering, well, you're being more down on exomoons, but I thought there was some hint of an exomoon or something in this paper. So this is we actually somehow ended up on the cover of this magazine. We didn't really want to, but we ended up there. The first title they said was Discovery of a First Exomoon. And we're like, no. That's not where this is. We think I have something interesting, but it's not that. So this is going back to the weird philosophy, I guess. When we look at these 284 Kepler planets, and we just measure how much out-of-transit signal is there, how much depth is there out of transit, this one object out here does have a 4 sigma interesting thing going on. However, if you look here, there is something at -4 sigma as well, very carefully. So you might think, well, this is just an outlier. It's not particularly surprising. But we were kind of desperate at this point for something interesting to follow up. So we were like, why don't we look at this a bit more closely? It does have, one thing I've always liked about this planet is many of the properties are kind of what I would intuitionally expect a moon hosting planet to have. It's on a nearly circular orbit. It goes around its star once every 300 days. It's a sun-like star. And the radius is pretty much 1 Jupiter. We can actually fit a mass as well, but those properties aren't particularly important right now. The only thing that's really bizarre is the size of the moon would be Neptune size. This instantly makes you recoil and think something's odd about it. But nevertheless, we thought it was interesting to pursue. We didn't feel convinced by that detection at that point, so we asked for some Hubble time to pursue it. And Alex Tichy led the observations, my graduate student, and fortunately we were granted the time to check out the subject.
What do you mean when you can fit a mass? With a moon? Or?
Yeah, we fit a photodynamical moon model to this, and we can get out masses, but I'd take those with a grain of salt at that point, because we just have 3 transits from Kepler, and that was it. Okay, so we observed with wide field camera 3 in photometric mode, and the instrument has some interesting peculiarities to deal with. 3 systematics in particular you have to worry about. This is in a paper by Hannah Wakeford. She points these out. There's this breathing effect, which is basically thermal variations through the orbit around the Earth. There's this visit-long slope, which is very important for this moon story. And actually, nobody really knows what's going on here, what causes this. It's not been correlated to any known onboard measurements on board HST itself. So it's not really, this could just be the star varying over time. It could be astrophysics. But it could also be something on the instrument we don't yet fully understand. And then there's this hook effect, which is well characterized. This is charge trapping happening in the detector and affects the sensitivity. Okay, so the breathing's super easy to get rid of, or at least the easiest of the 3 to get rid of, I'd say. This is our these are a movie of our images. This is Kepler 1625 in the middle, and you can see it's really obvious, the breathing, and it affects the entire plane of the detector homogeneously, basically. So you can just take a median brightness of this image and subtract it off, and it does a beautiful correction for that effect.
What are the units here?
Sorry?
What are the axes?
What are the axes? This is pixel position in X and pixel position in Y. Just literally a sky image, these things. The hooks, so then we do photometry. You draw a box around your star, you do photometry. We just do a simple aperture photometry, no PSF modeling, nothing super complicated. That's pretty much the convention for this type of work as well. This is the raw photometry of our target. This is the raw photometry of a comparison star up at the top. It's actually this guy. It's that comparison star. We can't use these because they clip off, unfortunately.
Not really a really naive question.
Yeah.
About the fact that I've never do observations. The smearing, is that just...
Oh, good question. That's because we go through a GRISM. So wide field camera 3 is really meant for doing exoplanet spectroscopy. Well, it's not specifically for exoplanet spectroscopy, but for spectroscopy in general. So it's spreading out the light. So you have sort of the red end of the spectrum over here and the blue end over here. So if you want to do spectroscopy, you can do that. We do a little bit of that in the paper, but really we just draw a box around the whole thing and just say we want all the light. All the light's important to us. We correct for these hooks. This is the conventional way of correcting for the hooks. You just fit an exponential trend, basically, on each orbit. This is pretty much what everybody does. It does pretty good, 444 ppm. This is what the comparison star looks like. But we actually came up with a new method. You can ask me about it afterwards to save time, but it's actually a completely non-parametric approach for removing these trends, and it works beautifully. It gets us down to 375 ppm, and similarly on the comparison star brings it right down. So we're pretty happy with the final photometry we get. It's actually almost 4 times superior to Kepler in terms of precision. It's almost what you'd expect given the aperture difference between the two. And there's something interesting here. At this point we were like, did we screw up? What's going on? Why is the star doing that at this moment in time? But it wasn't enough to get too excited about, to pop champagne open or anything, but it was kind of curious what was going on here. And then we started to fit it. Now when you fit it, you still have this long-term trend that's present in the data. And what we knew is that the hook effect occurs on a very different timescale to the moon effect. So we don't expect any strong covariance between the parameters which describe the hooking and the parameters which describe the exomoon. But the long-term trend happens on a much more important timescale. It actually significantly affects the depth of this dip on the outside here. Whether you use a linear model for the trend, a quadratic model, or an exponential model, you get quite different depths by a factor of 2. So clearly the long-term trend model is having a very important effect on the inference of this exomoon potentially signal. That means that when you do the fits, of course, it's very important to do a joint fit. Fit everything simultaneously, which is what we do. This trend model is interesting. This is a somewhat unprecedented observation. Nobody has observed an exoplanet for this long before with Hubble. I think that's true. We observed for 40 hours. We actually hit 2 visits, so that means that we had to reacquire the star at this point. That's why you see that kink. The star ends up at it's like 0.1 pixels offset after this reacquisition. This is about 13 orbits here and then another 13 orbits of HST on this side. But in the post-transit data, seems to be something interesting going on. However, I kind of cheated here because I have implicitly assumed a planet plus moon plus trend model. That is the model which I've regressed here. So what about just a planet on itself, by itself, with a trend? Get rid of the moon. So this is where the Bayesian evidence comes in. A key secret is don't ever use reduced chi-squared or anything like that for this kind of thing. You can't use reduced chi-squared for nonlinear models. It doesn't make any sense because you don't actually know the number of degrees of freedom in your model. It's ill-posed. There's a great archive paper called The Do's and Don'ts of Reduced Chi-Squared, if you've never read it, which goes all through exactly how you have to be very cautious using these kind of simple metrics, and evidence is really the best way for comparison. We tried 4 different models: ZP, planet; T, transit timing variations, but we don't assume what it is. It's just something's causing transit timing variations. M, which is the moon model, and then Z, which is a moon model, except we fix the moon radius to 0 radius. So this is a kind of an artificial model, but basically by comparing these 2 models, I can directly measure the significance of the dip itself. That's the only thing which changes between those 2. So when we go through this, we try different trend models. This is what everybody in the literature has done to date, linear and quadratic trend models. We introduced a 3rd model just for sake of comparison. And what we find is no matter what we do get strong evidence for this moon model. Very, very strong evidence for the moon model over a planet-only model. What's responsible for that? There's 2 effects. There's this transit timing effect we see. So actually the transit came in 78 minutes too early. That's quite a lot. It's quite a big early transit coming in here. This is the Kepler data, 1, 2, 3. If you draw a linear ephemeris through it, it should be on here. This is more than 3 sigma deviant at this point. We actually think the signal to noise of this is 4.3. And then there's this dip. Now remember that we're saying that the transit comes in early. That dashed line is where it should come in, and the solid line is where we measure it to come in, the midpoint. So it comes in early, and the moonlight dip is in late, which is exactly what we would expect for a photodynamical model. So that's kind of somewhat convincing at this point. And then the signal to noise of this also seems not overwhelming, but interesting, a signal to noise of 5. Okay. So I think a lot of it hangs on that dip. The TTV, you could always explain the TTV in other ways. A lot of it hangs on that dip. And really, we don't know exactly how to quantify the confidence in that dip, because ultimately it's the unknown unknowns that we can't measure and characterize, right? What we can say is that if you look at the centroid position of the star, it's very, very stable when the moonlight dip happens. It's right here. Nothing changes. We're way outside of a South Atlantic anomaly, so we don't think that's affecting us. We see the moon dip in the blue channel and the red channel of our data. The solution is physically self-consistent in terms of the masses and radii. And when we look at the residuals are perfectly flat except for right here, where the moon is. This is assuming no moon. So if you assume no moon, the residuals behave perfectly Gaussian except for this moment in time when something goes weird. Whereas if you assume a moon, you get really well-behaved residuals. So as far as we can tell, we've tried all the checks we can really think of, but ultimately, I don't think the case is closed on this. Because the HST data is so good, actually, it's so much more precise than Kepler, it basically overwhelms the regression. So really, we only have 1 data point, I would say, for this exomoon. Also, what's kind of concerning is when we revise the Kepler data with the new data release 25. When we did our original analysis, it was on data release 23. Going from 23 to 25, even the Kepler data, the moon appears a little bit less apparent. So that concerns us. We don't have any post-moon transit data, right? The moon seems to just come in and then we don't see it afterwards. If we had another 40 hours of data and we saw the flux return back up to normal, that'd be much more convincing. We don't have that. So that bothers me. And of course, this moon's bizarre. This is a Neptune radius moon still. at this point. So it's still very peculiar and certainly not anticipated, much like hot Jupiters from a formation perspective. On the plus side, these signal to noises are kind of interesting, 4 for the TTV, 5 for the dip. And it's a long period Jupiter, of course, which is exactly what we'd expect for a moon hosting object. The moon hypothesis explains both pieces of evidence with one single hypothesis. So in that sense, it's kind of elegant that it can explain both. As far as we can tell, the dip does not appear to be instrumental. We did all these checks I mentioned, and we don't see anything odd going on. And finally, we get this self-consistent solution. Like the mass of the moon comes out to be a Neptune mass, and the radius is a Neptune radius. And that's not imposed by the model. It naturally converges to self-consistent solutions. So those things are interesting. But I still wouldn't call this a discovery or anything. This is just evidence, interesting. We hope other people will continue to look at this object and pursue it. We're writing a follow-up paper about follow-up opportunities actually right now, about how this object could be confirmed or refuted in the future. But for right now, I think more data is necessary to really clean up this case. But at least we're getting to the point where we are seriously talking about detecting exomoons. We have interesting signals, which at least is something. At least we're moving the bar along in terms of our ability to look for these things. OK, so I'm almost out of time. So I'm going to try and skip closely through one more project about looking for the very strange things. What about things which aren't moons? Moons are kind of weird, but they're not that weird, I guess. What about something that's algorithmically like this? Like how do I look for Tabby's star in Kepler data? Well, it's actually done by people before. People use this Planet Hunters website. They looked through lots and lots of images, and they started to see something strange. How do you do that automatically? Well, you have to write down a merit function if you want to search for something like this to classify a strange signal. Conventionally, what you probably would do in the exomoon case, is you have some model that you're trying to regress to your data, and then you write down a likelihood function once you have the model, say least squares in this case, basically minimizing the chi-squared. The problem is here you don't have a good model. Before you see that, you don't know what the model is. So really, ideally, it's kind of paradoxical, but you want the data to teach you what the model is, rather than assuming you know what the model is beforehand. There is a way of doing that based off a technique called phase dispersion minimization. It's used in pulsar timing quite a bit, actually. So if you consider a periodic signal that's weird, this is our weird signal. This actually could be like a lens, for instance, in this case. If you fold it on the correct period and take the running average, the scatter about that running average is smaller than it would be if you did it just about the flat line, right? Because it's coherent. There is coherence in this signal. So what if we could design a metric to look for coherence? Well, that's basically just the chi-squared against that yellow line. That's phase dispersion minimization. It works pretty well. The period here is 36 days, and indeed you get a peak at 36 days doing this. So that seems to work. The problem with PDM alone is that it returns many rotating stars. I don't want rotating stars. They're boring. I want really interesting stuff. I want stuff which is spiky and sharp and short duty cycle. So how do we get rid of those sorts of things? There's kind of a neat trick my student Adam Wheeler down here came across, that you can look at the tailedness of the distribution. So this is, again, the signal. When I folded it on an incorrect period here, I phase binned the data and then take a histogram of it. And it's basically symmetric, as you might expect, because this is just, the data essentially looks like random noise if you fold it on the wrong period and bin it. But if I bin it on the correct period, you pick up that spike, and you see this very high-tailed distribution. It's also skewed, but you don't want to just use skewness, because that assumes that it has a particular symmetry. But if you use kurtosis, you can actually pick out these whatever up and down, or however they're distributed, pretty well. So Gaussian noise has a kurtosis of 3, a sine wave is 1.5, but a box transit, for instance, can become huge. This is like the duty cycle of the event. So d to the minus 3. So a very short duty cycle event has a huge kurtosis, actually. OK, so what we do is in the weird detector, as we call it, up here is our code. It's PDM multiplied by kurtosis. So it's this multiplied by this, basically, as our merit function. And then we bootstrap for significances. So pretty simple. We run it through 200,000 Kepler stars. We see some interesting stuff. This is a comet that's passing through the field of Kepler. So we pick up these 3. These are all one-offs, actually. They're not strictly periodic, even though we're optimized for periodic events. So really the kurtosis effect is picking this up. We see these events here, here, along these points. And this is actually the ephemeris from JPL of a known comet that, as you can see, is very, very close. The reason why it's not bang on is because this is in geocentric coordinates and Kepler's Earth trailing. We didn't go through the actual correction, but I think it's pretty obvious that this is what's responsible for this event, so you can actually see comets passing through the field. We also see a bunch of other stuff. Of course, we recover all the KOIs, which is nice. We get Tabby star back. And we also get these 18 new signals, which have not been seen before. These are pretty interesting. I think we hypothesize these are most likely heartbeat binaries, or maybe even heartbeat planets, perhaps planets on eccentric orbits, which are tidally exciting the star at periapsis as they come in. And we're trying to actually, the referees asked us to try and regress some proper models to these, which is what we're working on now. But otherwise, this paper is pretty much baked, so we're just trying to figure out what these things exactly are. But if you have ideas, interested to hear. So I think because I've run out of time, I should probably stop there. And I just want to advertise Alex Ticci's work, who led a lot of the Exomoon research. This is Adam Wheeler, who led the weird detector. And we have another project which I encourage you to look at, unfortunately I didn't have time to talk about, by Emily Sanford, that's been thinking about how to interpret these types of signals as well in a non-parametric way that we call shadow imaging. So I just thought they'd just have some time for questions. All right, thank you.